Hello, in this video we'll be working through Unit 5 homework problems 29 through 35. For number 29, we're given the graph of the position function of a particle moving along the x-axis. So this is the graph of P of t, the position of the particle. And the position is measured in centimeters, t is measured in seconds. For what interval of time is the particle moving to the right? The particle is moving to the right when the velocity is positive, and the velocity is positive when the position is increasing. Since I'm looking at the position graph, I'm looking for the places where this graph is increasing. So that would be here, and that's the only time it's increasing. So for part A, we can say the particle is moving right, on the interval from 0 to 1, since P of t is increasing. Part B, for what intervals of time is the particle moving to the left? Well, that would mean velocity is negative, which means position is decreasing. So the position graph is decreasing here and here. So part B, the particle is moving left on the intervals 2 to 3, union 5 to 6, since P of t is decreasing. Part C, express the velocity as a piecewise defined function on the interval from 0 to 6. So I have 1, 2, 3, 4, 5 pieces. I've got the piece from 0 to 1, the piece from 1 to 2, the piece from 2 to 3, piece from 3 to 4, from 4 to, from 3 to 5, 3 straight on to 5, and then from 5 to 6. Okay, so I am writing an equation for V of t equals, and I have a lot of pieces. So the first piece, the velocity is the slope of the position. So the slope between 0 and 1 is positive 2. So 2, and that occurs on the interval from 0 to 1. Now I should use t, not x. Now should we include these endpoints? Well, the velocity is going to be undefined wherever the position is not differentiable, and it's not differentiable at endpoints and at corner points. So our velocity is undefined at all these points I'm circling, the 2 endpoints and then those interior corner points. So we are not going to include the 0 or the 1 for our velocity function. Velocity is undefined at 0 and at 1 and 2 and 3 and 5 and 6. Okay, so our second piece is between 1 and 2, and the slope of the position there is 0. So my velocity is 0 on the interval from 1 to 2. My slope is, so we go down 4 and over 1, so negative 1/4 on the interval from 2 to 3. Nope, we go down 4 over 1. That's not negative 1/4, that's negative 4. Okay, and then my slope between 3 and 5 is 0. And finally, between 5 and 6, the slope there is down 2 over 1, so negative 2. Okay, there's my piecewise function for velocity. Part D, at what values of t is the velocity undefined on the interval from 1 to 6? So I mentioned that already. It's undefined at the endpoints. So V of t undefined at t equals 0, it's an endpoint, and then all my corner points, 1, 2, 3, 5, and my other endpoint, 6. And part E, find the average velocity of the particle on the interval from 1 to 6. average velocity is going to be p of 6 minus p of 1 over 6 minus 1. We have the graph of p of t, so p of 6, I'm just reading that point off the graph. So at 6, p is equal to negative 4. Negative 4 minus p of 1. At 1, p is equal to 2. Over 6 minus 1 is 5. So I have negative 6 over 5. This is average velocity. So in my numerator, I have change in position. That was centimeters. In my denominator, I have the change in time, which was seconds. So my velocity is measured in centimeters per second. Number 30, a particle moves along the x-axis so that at any time t between 0 and 5, the velocity in meters per second is given by v of t equals t minus 2 squared times cosine 2t. Use your calculator to determine how many times on the interval from 0 to 5 the particle changes direction, and give a reason for your answer. So the particle is going to change direction whenever the velocity changes sign. So we're looking for the places where v of t changes from negative to positive or positive to negative. So I'm just going to say in general wherever it changes sign. So let's look at a graph of our velocity and see where it's changing sign. My velocity equation, t minus 2 squared times the cosine of 2t. And we want to make sure we're in radian mode for this. And we'll try just a standard window. Wow, lots going on there. We only really have to look on the interval that we were given, and that was for times 0 through 5. So let's make our x min 0, our x max 5, and see what we get there. Okay, and then how many times does this graph change sign? Well, it changes sign right before 1, and then somewhere between 1 and 3, and then somewhere just before 4. But I'm going to zoom in really close on the middle part of this graph here. Let's tighten up our y min, y max. Let's see if we can do, well, let's just do negative 1 to 1. So it's still looking like 3. We've got one right here, the next one right here, and the last one over here. And it turns out that if we zoom in even closer, there is something, there's a little dip right here, so something weird is happening in there. I want to get an even closer look. So right now my y values are going from negative 1 to 1. I'm going to get really close. Let's do like negative 0.2 to positive 0.2. Okay, so we actually have 1, 2, 3, 4 x-intercepts on this interval. However, at t equals 2, yes, there's an x-intercept there. The velocity is 0, but it doesn't change sign. It's negative until we hit 2, and then it's negative after that as well. So because there's no sign change there, it doesn't count as a change in direction. The particle is momentarily at rest, but it's not changing direction. So we have 1, 2, 3 changes in direction like we initially thought. Part B, using appropriate units, find the value of v prime of 2. Describe the motion of the particle at this time. Well, we already have a hint of what's happening at 2 because I'm looking at my velocity graph. And at 2, let me just hit trace 2, enter. So our cursor jumps right to that point. So at 2, the velocity is 0. So our particle is at rest. And we can see that we do not have a sign change. So it's not changing direction. It's just momentarily at rest. And then it's going to continue to move to the left. The velocity is negative on either side of that point. So the particle is moving left. But let's answer the other part of the question. What's v prime of 2? So I have v of t in my y1, and if I want to find the derivative of that at 2, I can use Math 8 to do that. So I'm going to go back to my home screen. Math 8, I want the derivative with respect to x. of y1. My velocity equation is in y1. So alpha f4, y1, and then I want to find this derivative at a value of 2. Okay, so here's my answer, 1.5 times 10 to the negative 6. So not quite 0, but really close to 0. If we round to 3 decimal places, we get 0. So it's approximately equal to 0. And the units on this, v prime is acceleration. So our units here would be meters per second, or meters per second squared. So let's say approximately 0 meters per second squared. And we said the particle is momentarily, just at that one instant, momentarily at rest, but not changing direction. Since v of 2 equals 0, but I'm trying to say the velocity is negative on either side. Well, I'll just say, but v of t does not change sign. At t equals 2. And part C, using appropriate units, what is the average acceleration between t equals 1 and t equals 3.5 seconds? So average acceleration is the change in velocity, v of 3.5 minus v of 1, over the change in time, 3.5 minus 1. So here, I still have my velocity equation in y1. So I just want to find y1 of 3.5 minus y1 of 1. So let me quit. And let me go into my fraction F1 menu. And I can do y1 of 3.5 minus y1 of 1 over 3.5 minus 1 is 2.5. Okay, so that's about 0.845. 0.845. That's my average acceleration, and acceleration, the units are meters per second squared. 31. Jeff leaves his house riding his bicycle toward school. His velocity, v of t, measured in feet per minute, on the interval from 0 to 15 for t minutes is shown in the graph below. Find the value of v prime of 4. So we are looking at the graph of v of t. We want v prime of 4. That's the slope of v at 4. So at 4, we're right here on our velocity graph. What is the slope at that point? Well, I can use these two corner points to get my slope. So I've got the point 3, 35 and the point 5, negative 35. So the slope there would be negative 35 minus 35 over 5 minus 3, or negative 70 over 3. V, the units for V are feet per minute, so V prime is going to be feet per minute, or feet per minute squared. And this tells us how quickly the velocity is changing at that moment in time. So we could say the velocity is decreasing at a rate of 70 over 3 feet per minute squared at time t equals 4 minutes. Part B, on the interval from 0 to 5, is there any interval of time at which the acceleration must equal 0? So remember that acceleration is the derivative of velocity, and we're looking at the velocity graph. So we're asking, is there anywhere the derivative of this graph must equal 0? Well, that sounds like Rolle's theorem. But we have the graph, so we can just look and see. I mean, it's not really asking us, is it guaranteed in this question? It's just asking us, is there anywhere the acceleration is 0? So on the interval from 0 to 5, we're only looking at like this part of the graph right here. Is there any point in time on that interval where the acceleration is 0? So the derivative of velocity is 0. Yes, right here, the derivative of the velocity is 0. So between times 2 and 3. So for part B, we can say, yes, on the interval 2 to 3, a of t equals 0, since, I would just say the slope of the velocity, so v prime of t equals 0, or there's a horizontal tangent line. Now part C says, on this interval from 0 to 5, let me erase some of this stuff. So on the interval from 0 to 5, does Rolle's theorem guarantee there will be a value of t such that the acceleration is 0? We already know that there is somewhere the acceleration is 0, but is it guaranteed by Rolle's theorem? Well, Rolle's theorem has 3 conditions that must be met. So one of our conditions is that on our interval, 0 to 5, the function has to be continuous, and it is. If we were to trace this graph from 0 to 5, we don't see any discontinuities. So yes, it's continuous. Is it differentiable on the interval from 0 to 5? Well, no, it's not differentiable here or here, and it only requires one place where it's not differentiable. It fails that condition. So no, Rolle's theorem does not guarantee that. It also fails the last condition. At the end points, we'd have to have the same y-coordinate. And at 0, v is 0. At 5, v is negative 35. So we failed 2 out of 3 conditions. We definitely cannot apply Rolle's theorem on the interval from 0 to 5. Part D, at some point Jeff realizes that he forgot something at home and has to turn around. After how many minutes does he turn around? Give a reason for your answer. Well, again, this is our velocity graph. So wherever the velocity is positive, he's moving to the right, or he's moving away from his point of origin. Okay, so we're positive, 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 until we get to time t equals 4, right here. Then we're not positive, we're 0 and switching to negative. So after that point, we're negative. So he's moving away from his point of origin until time 4, and then towards his point of origin from between time t equals 4 and time t equals 10. Now this graph isn't a very realistic model of his motion, because according to this graph, at time t equals 4, he instantly changes direction while maintaining a constant acceleration. And that would probably be a pretty difficult feat on a bicycle. But according to our graph, that's what is happening. Number 32, a particle moves along the x-axis so that its velocity at time t is given by v of t equals negative t plus 1 times the sine of t squared over 2. Find the acceleration of the particle at t equals 2. So let's start there. This is a calculator active question, and the acceleration is just the derivative of the velocity. So we can get the acceleration at 2 using Math 8 on our calculator. I'm going to enter my velocity equation. So negative t plus 1 times the sine of t squared over 2. Again, make sure you're in radian mode there. And we'll just try a standard window. Okay, that looks interesting. And we're trying to find the acceleration at time 2, and I'm going to do that using Math 8. So derivative with respect to x. I want to take the derivative of my velocity equation, so I'm going to hit y1. And I want that derivative when my input value is 2. So I get 1.587 or 1.588. 1.588. A of 2 equals 1.588 is the speed of the particle increasing at t is equal to 2? Well, we know the acceleration is positive at 2. What is happening with the velocity at time 2? So looking at my graph, it looks like it's negative, but let's verify that. I'm just going to hit trace 2, enter. And yes, I can see that at time 2, the velocity is negative 2.728. Negative 2.728. Which is negative. So at time t equals 2, the acceleration and velocity have opposite signs, and that means that the particle is slowing down. So is the speed increasing? No, it is not. The speed is actually decreasing at that time. The speed is decreasing, or we can say the particle is slowing down at t equals 2, since v of 2 and a of 2 have opposite signs. And then part B, find all times on the interval from 0 to 3 when the particle changes direction. So for that, I want to know when my velocity changes sign. So I want to look at my velocity graph on the interval from 0 to 3. So let's fix our window. We're just going to look from 0 to 3. And how many times do we get a sign change in the velocity? It looks like that only happens once, but I'm going to zoom in a little bit closer to make sure we don't get a sign change like between 0 and 1/2 here. So let's make our y min negative 0.5 and our y max 0.5. Okay, so nothing strange going on there. I get one change in sign in my velocity somewhere between 2 and 3. And we're asked to actually find that time. So that's going to be the 0 on this graph. Let me get a better window. I'll go back to negative 2 to 2. And I want to do second calc. We can choose 0. And that value is approximately 2.507. Justify your answer because velocity changes sign, or we could say from negative to positive at that time. Number 33, the graph of the velocity v of t in feet per second of a car traveling on a straight road for time 0 to 50 is shown below. A table of values at 5-second intervals of time is also shown. During what intervals of time is the acceleration of the car positive? We're looking at the velocity graph, so acceleration would be the slope of this graph or the derivative of this graph. During what intervals of time is the acceleration positive? Acceleration is positive when velocity is increasing. So just looking at our velocity graph, when is it increasing? It's increasing starting at 0 and all the way up until we reach time here, so 35. So on what interval of time is that happening? It's happening from 0 to 35. And then my velocity is also increasing between these two times, from 45 to 50. Okay, so since v of t is increasing. Part B, find the average acceleration of the car over the interval 0 to 50. Average acceleration, we want v of 50 minus v of 0 over 50 minus 0. From the table, I can see that v of 50 is 72 and v of 0 is 0. So we have 72 over 50. The velocity is feet per second, so the acceleration would be feet per second, or feet per second squared. Part C, find one approximation for the acceleration of the car at t equals 40. So we know the velocity at 40 is 75, but we want to estimate the acceleration at that time. So we can use the closest two surrounding points, finding the slope at those two endpoints, and that will give us the average rate of change in my velocity, which is average acceleration. So for that, we're going to do the velocity at 45 minus the velocity at 35 over the difference in times of 45 minus 35. So that's negative 21 over 10, or negative 2.1. And this is, we're estimating acceleration, average acceleration. So again, that is feet per second squared. And part D is the speed of the car increasing or decreasing at time t equals 40. So I'm going to look at the graph for that. I think it'll be easier to see on the graph. At t equals 40, we're looking at this point right here. The velocity is positive and it's decreasing. So the velocity at t equals 40 is positive and decreasing. Therefore, the speed is decreasing. The acceleration, since velocity is decreasing, that means this acceleration is negative. And when velocity and acceleration have opposite signs, the speed is decreasing. So it might be tempting to use our answer from part C to try and answer this question, but the average acceleration doesn't necessarily guarantee. If your average acceleration is negative, wait, was ours negative or positive? Look back at that a second. It was negative. Our average acceleration was negative. But that's not going to guarantee that the acceleration was negative everywhere on that interval. So the graph is a better way to answer that question. Number 34, two runners A and B run on a straight racetrack for times t between 0 and 10 seconds. The graph below, which consists of two line segments, shows the velocity, okay, this is velocity graph, of runner A. The velocity in meters per second of runner B is given by the equation v of t equals 24t over 2t plus 3. So for runner A, we have a velocity graph, and for runner B, we have a velocity equation. Part A says, find the velocity of runner A and the velocity of runner B at t equals 2 seconds. So we want, let's say runner A, we want to find the velocity at time t equals 2. So we want v of 2. We have the velocity graph for runner A, so at 2, just read that point off the graph. Okay, so that's going to be hard for me to estimate. On my screen here, it looks like it might be 6, but that vertical line wasn't very vertical. It might be actually somewhere between 6 and 7 there. So I can get this for sure if I figure out the equation of this line segment right here. And since I have 2 points passing through that line, I can get the equation of that line. So the slope of that line would be 10 minus 0 over 3 minus 0, or 10/3. Okay, so I don't know if this is considered cheating or not because I'm not really using the graph. I'm converting the graph back into an equation. So I have 10 over 3 is the slope times t plus the y-intercept, and the y-intercept is 0. So that's just it. That's the equation for that piece of the graph. And when I put 2 in for t, I get 20/3. So v of 2 equals 20 over 3, which is really close to 7. It's closer to 7 than it is to 6. Right, that's 6 2/3, so 6.6 repeating. And the velocity there is given in meters per second. For runner B, we're going to use the equation that we were given for runner B. I guess I should have called this one something other. Let me call it V sub A to avoid confusion there. Runner B, my equation up here, I'm going to call that V sub B. And to find V of 2, I'm going to substitute 2 into that equation. So 24 times 2 over 2 times 2 plus 3, or 48 over 7. So 48 goes, or 7 goes into 48 6 times. That's 42 with 6 left over. So we have 6 and 6/7. Let me go ahead and just compute that. This is a calculator active question. So 48 over 7, 6.857 meters per second. So it's easier to compare the two decimal values to see who is running faster at that time. For part B, we're asked to find the acceleration of runner A and the acceleration of runner B at time t equals 2. So for runner A, using the graph of velocity, we're going to look at the slope at time 2, which I have already computed. A of 2 would be the slope of the velocity at t equals 2, and that's 10 over 3, or 3 1/3, 3.3 repeating. For runner B, since we have the velocity equation, then the acceleration is going to be the derivative of that. So let's get our acceleration equation for runner B. To take the derivative of this velocity equation, I'm going to use quotient rule. So derivative of the top times the bottom minus the top times the derivative of the bottom over bottom squared. I'm not going to bother to simplify. I'm just going to go ahead and substitute in. I want the acceleration at time 2. So the acceleration when t is 2, let's do 2 times 2 is 4 plus 3 is 7. 24 times 7, okay, maybe I'll get the calculator out for that. 24 times 7 minus, and then here we have 24 times 4, and then over 7 squared, so over 49. I can factor a 24 out of the top, might make it a little bit easier. So it's 24 times 7 minus 4, and then over 49. It's 24 times 3 over 49. .469. And the acceleration would be meters per second squared for both of those. Number 35, an object moves along the x-axis with initial position x of 0 equals 2. The velocity of the object at time t greater than or equal to 0 is given by the function v of t equals sine of pi over 3t. What is the acceleration of the object at time t equals 4? Since we have the velocity equation, we can get the acceleration equation by taking the derivative. We're going to try this one without using the calculator. So a of t would just be the derivative of sine of pi over 3t. We need to use the chain rule here. Derivative of sine is cosine. So cosine of stuff times the derivative of the stuff, which is just pi over 3. Now the acceleration at time 4 would be the cosine of 4 pi over 3 and then multiplied by pi over 3. the cosine of 4 pi over 3. So that's 3 pi over 3 here, plus another pi over 3. It puts us down here. We're in quadrant 3 where the cosine is negative. So negative 1/2 times pi over 3, or negative pi over 6. Part B, consider the following two statements. Statement 1, for time between 3 and 4.5, the velocity is decreasing. Statement 2, for times between 3 and 4.5, the speed is decreasing. Are either or both of these statements correct? For each statement, provide a reason why it's correct or incorrect. Statement 1 is asking us about the velocity. Well, we could try and work with the velocity. We could try and work with the acceleration. If we want to know when the velocity is decreasing, that would be when the acceleration is negative. So let's look at our acceleration equation again. We had pi over 3 times the cosine of pi over 3t. I'm going to set this equal to 0 and solve. So this will equal 0 whenever the cosine of pi over 3t is equal to 0. And cosine is 0 at pi over 2. Remember, we're working on the interval t greater than 0. So we'll say at pi over 2, cosine is 0 at pi over 2, and then also at 3 pi over 2. So the angle that we're taking the cosine of is pi over 3t. So if that's equal to pi over 2 plus 2 pi k, or if that's equal so if that angle is equal to 3 pi over 2 plus 2 pi k, then my acceleration will be 0. And let's solve for t by multiplying both sides by 3 over pi. So we get t equals, if I multiply pi over 2 by 3 over pi, I get 3 over 2, plus, and then here I'm also multiplying by 3 over pi, which just gives me 6k. And then over here we multiply through by 3 over pi, so that gives me 9 over 2 plus, and then I multiply my 2 pi by 3 over pi, which again gives me the 6k, for some k in the set of integers. So 3 over 2 is 1.5. 9 over 2 is 4.5. I have a critical value at 1.5, and then the next critical value is at 4.5. So if we make a number line, 1.5, there's another next critical value at 4.5, and then pick a test point in between. This is where the acceleration is 0, and nowhere else between 1.5 and 4.5 is the acceleration 0. So in between, it must be entirely positive or entirely negative. So let's just pick, and again, we're working with a trig function, so I'm not going to pick 2. I'm going to pick something that's kind of easy to test between 1.5 and 4.5. Well, pi is about 3.14, so that's in between there, and pi should be fairly easy to check. Actually, no, it won't be, because we have to substitute it in here. How about 3? 3 would be good, because then if t is 3, it would cancel with the 3 on the bottom. So yeah, let's check 3. So now if I put 3 into my acceleration, pi over 3 times 3 is just pi. The cosine of pi is -1, so I get a -1 times pi over 3. That's negative. So acceleration is negative here. And we're asked specifically what's happening between 3 and 4.5. So between 3 and 4.5, I can see that my acceleration is negative. So a of t is less than 0, therefore v of t is decreasing that means statement 1 is true. Statement 2 is asking about the speed of the object. So we already know the acceleration is negative that entire time between 3 and 4.5. What do we know about velocity on that time interval? So we need to know if the velocity between 3 and 4.5 is always negative or always positive, or does it change somewhere in there? So if I want to know when velocity is positive or negative, I'm going to set it equal to 0 and solve. My velocity is sine pi over 3t. I'm going to set that equal to 0 and solve. Well, sine is equal to 0 at 0 and at pi and at 2 pi. So 0 plus 2 pi k and pi plus 2 pi k. And that's equal to the angle I'm taking the sine of. So pi over 3t equals one of those two options. And to solve for t, I'm going to multiply again through by 3 over pi. So 0 times 3 over pi is still 0, plus, and then the 2 pi gets multiplied by 3 over pi, and I get 6k. And then for my other solution over here, I get t equals pi times 3 over pi is just 3 plus 6k. So I have critical values at 0 and 3. And we're interested in knowing what's going on between 3 and 4.5, so I feel like I probably should find my next critical value as well. The next critical value after 0, so here I've got, my solutions look like 0, 6, 12, dot, dot, dot. So there's a critical value at 6. And over here, I've got 3, and then we add 6 to that, we get 9, and then we add 6 again to that, and we get 15, etc. So 6 would be the next one. So I'm checking my velocity. I know the velocity is equal to 0, at 3, and at 6. And we want to know what's happening on the interval from 3 to 4.5. So really, I only have to check between 3 and 6. So think of a good number between 3 and 6. Well, if I want to get this 3 to cancel out on the bottom, ideally I would choose 3 or 6, but I can't choose an end point. So I want to choose something between 3 and 6. Let's choose 4, because then I'll be taking the sine of 4 pi over 3, and that is a special angle, so I can find that. I'm going to use 4 as my test point. So the sine of 4 pi over 3. We saw 4 pi over 3 earlier. It's right here. So the sine is negative, and then my reference angle has a sine of root 3 over 2. So the velocity at 4 pi over 3 is negative. That's all I really need to know, is that it's negative. Velocity is negative on this interval, and the acceleration is also negative on this interval. And since they both have the same sign, speed is increasing. Speed is increasing. However, the statement says that the speed is decreasing, so that is a false statement. Statement 1 is true. Statement 2 is false.